We often look up at the night sky and ask, who arranged all of this? Let me guess you're thinking, God, aren't you? We naturally assume there must be a master, a great architect, keeping the Earth in orbit. But consider this. Our entire understanding of the universe is actually a house of cards, built high upon a fragile scaffold of pre-existing theories. Inside this structure, modern scientists are no longer blind explorers on voyages of discovery. Instead, they are often just anxious workers trying to confirm predictions already made, hoping that a single new result doesn't topple the entire house. What if I told you there is no architect? What if the house stands on its own, supported only by cold, invisible mathematical rules? History warns us that we are often wrong. Most scientific theories eventually fail, ending up as dead and forgotten footnotes. Remember phlogiston? In the 18th century, it was the leading explanation for heat, taught by professors everywhere, until it was proven to be total fantasy, or the steady-state theory, which once rivaled the Big Bang until the evidence piled up and the lights went out on its last believers. The history of science is not a record of divine order, but a graveyard of wrong ideas. Today, we seek the most terrifying yet liberating answer. Can the universe operate like a perpetual machine, requiring only the rules, but no master? So if the universe runs on rules, not supervision, where do we see those rules push back against us? Not in a galaxy, not in a nebula, in the tiny wobble of a short-lived particle, hidden in a ring of magnets outside Chicago. In early 2021, before the press conferences and headlines, the scene at Fermilab was quiet in a very particular way. Not the silence of nothing happening, the silence of something irreversible about to be revealed. Down the hallway from an Illinois cornfield, inside a building that looks ordinary from the outside, stands a 50-foot diameter superconducting ring about 15 meters across. Inside that ring, scientists send beams of muons, particles about 200 times heavier than electrons, around and around at close to the speed of light. A muon carries charge, so it behaves like a tiny spinning magnet. The rate at which its spin precesses in a magnetic field, the subtle wobble of its compass needle, is described by a number called G. According to the simplest picture of quantum mechanics, G should be exactly 2. But the real universe is never that simple. Quantum fields nudge the value slightly away from 2, creating the anomalous part of the magnetic moment. That anomaly is a perfect place for the universe to disagree with us. For decades, theorists refined the standard model prediction for the muons G-2, taking into account known forces and particles. In 2020, an international muon G-2 theory initiative produced a consensus value, a prediction with uncertainty written only in the last few places. On the experimental side, the Fermilab team had spent years preparing the ring. They tuned the magnetic field to an astonishing uniformity of around 1.45 Tesla across the storage region. They cooled the apparatus to about minus 450 degrees Fahrenheit, just a few degrees above absolute zero, to keep the superconducting magnet stable. Then they began to send muons into orbit. Each muon is unstable. After about 2.2 microseconds in its own rest frame, it decays into other particles. In the lab, moving at relativistic speeds, those microseconds stretch out. As the muons race around the ring thousands of times, their internal magnets precess in the magnetic field, and the pattern of their decays carries information about how fast that precession is happening. Detectors lining the ring count the decay products and reconstruct the wobble. They do not see the muons directly. They see traces, pulses, timestamps, the shadows of a rule being enforced. By the time they had finished their first run in 2018, the collaboration had collected data from more than 8 billion muons. More than 200 scientists from 35 institutions in 7 countries spent years analyzing those events, cross-checking calibrations, testing assumptions, and trying to avoid the most ordinary kind of human mistake, seeing what they wanted to see. So they blinded themselves. A secret offset was added to the key measurement. The number the analysts looked at every day was shifted by an unknown amount. The true value was locked behind a code that only a few people held, written down and sealed away. Until the very end, the collaboration did not know whether the muon matched the standard model prediction or not. If there is no master tuning the universe, bias is what we add by hand. Blinding is a small ritual of humility, an attempt to keep our expectations from touching the data. On April 7th, 2021, they unblinded the result. A sealed envelope was opened. A code was typed into a computer. The hidden offset was removed. The universe did not line up. The theoretical prediction for the anomalous magnetic moment, the tiny difference between G and 2, was about 1.1659 times 10 to the minus 3. With a vanishingly small uncertainty, the new experimental world average, combining the Fermilab measurement with the earlier Brookhaven result, came out slightly higher than that, again with a similarly tiny uncertainty. The gap between those numbers is small. The implications are not. When statisticians folded in all the uncertainties, they found a discrepancy of 4.2 standard deviations, or 4.2 sigma. In everyday language, if there were no real difference, if the standard model were perfectly complete and the universe were just playing along a fluctuation, this large would be expected only about once in 40,000 trials. Not impossible, just very reluctant. That reluctance was enough to make hundreds of physicists sit very still. In popular coverage, people started using familiar phrases: evidence of new physics, hints of a fifth force. The idea was simple. If the muon is processing faster than predicted, perhaps there are additional quantum fields around it, additional interactions in the vacuum, slightly tugging on its magnetic moment. In other words, maybe the rulebook we call the standard model is missing a page. But notice what is actually happening here. No one in that hall in 2021 was watching a hidden hand reach into the experiment and twist the muons. No dial was turned when the envelope was opened. The particles did what they had already done months earlier, racing around the ring at nearly light speed and decaying according to whatever rules reality obeys. The only thing that changed in that moment was human knowledge. The wobble had always been there, set by interactions that either are in the standard model or are not. The blinding key did not affect it. Wishful thinking did not affect it. The personal beliefs of any of the 200 scientists did not affect it. The ring did not care. This is the quiet violence of precision physics. Our theories look solid, heavy, inevitable. They acquire an air of authority, especially when they have survived decades of tests. The standard model has predicted particle masses and cross-sections to many decimal places. It underpins the design of accelerators and detectors. It works, and then a number at the edge of that structure shifts in the fourth decimal place, and the whole thing looks less like a cathedral and more like scaffolding. The house of God, the comforting picture of a perfectly understood, perfectly supervised cosmos, doesn't crack because the universe breaks its own rules. It cracks because the rules are stricter than our stories about them. Muon-2 is not a rebellion. It is obedience to a deeper consistency we have not fully written down. Even the interpretation remains unsettled. After 2021, theorists revisited the calculations. New approaches to the underlying quantum field contributions appeared. Some groups found values closer to the experimental number, others did not. The disagreement between experiment and theory began to look less like a clean verdict and more like an ongoing argument between different ways of encoding the same quantum chaos. But the essential point for our question remains untouched. At Fermilab, the muons follow a path determined by fields, symmetries, and quantum fluctuations. They do not wait for permission. They do not consult the standard model. They do not adjust themselves to make our equations look elegant on a slide. When the data disagree with the prediction, nothing in nature is broken. Only our description is. If someone had wanted to preserve the neatness of the old picture, they could have looked at that 4.2 sigma and said, it's probably just a fluctuation. Or they could treat it as a crack at the edge of the map, a hint that the invisible structure we live inside is less simple, less closed than we once hoped. In that sense, the muon experiment is a small demonstration of life in a rule-only universe. There is no sign of a supervising presence stepping in to rescue the standard model. There is no special protection for our most successful theory. A particle's spin precesses according to whatever interactions exist, whether we have named them or not. Our best calculation is allowed to be slightly wrong. The house of cards stays up only as long as the cards balance. No hand holds them, and somewhere behind that anomaly, whatever its final interpretation, sit 4 familiar interactions we have given names to, and perhaps one more we have not yet understood, all pulling on the muon's tiny magnet without asking anyone's approval. The muon's wobble hints at crowded, invisible company. To see who is pulling on it and on you, we only have to look at the most ordinary thing in the universe, a body resting on a chair. Right now, as you sit or lie or lean somewhere, 4 vast rule systems are negotiating over every atom in you. Not one of them knows your name. One of them is trying to drag you into the center of the earth. One of them is holding you up, refusing to let you fall through the chair. One of them is gluing your atoms together so tightly that your body behaves as a solid instead of a cloud. And one of them, mostly in silence, is rearranging particles inside atomic nuclei and powering the star that set the day-night cycle that your body lives by. We call them forces. It might be more honest to call them constraints. Gravity, electromagnetism, the strong nuclear interaction, the weak nuclear interaction, 4 managers that never meet, 4 rulebooks that never consult one another, each carving out its own domain. Start with the one you feel most clearly. Gravity keeps your feet on the floor and the moon in orbit and the Earth tethered to the Sunday. It is the curvature of space-time around mass and energy, a geometric rule written into the stage itself. You do not turn it on in the morning. You do not ask for it. You only notice it when you try to fight it. Push up from the floor with your legs. You feel effort, strain, resistance. Gravity feels strong in that moment. It feels personal. You are struggling against it. But that feeling is a local illusion. Compared to the other 3 interactions, gravity is feeble, almost beyond imagination. A small refrigerator magnet on a door can lift a paperclip and hold it there. That tiny patch of magnetized metal, driven by electromagnetism, is defeating the gravitational pull of an entire planet with a mass of roughly 6 times 10 to the power of 24 kilograms. A sliver of electromagnetic order, localized in a few cubic centimeters, overwhelms the pull of all the rock and iron beneath your feet. Your little finger can do something similar. The electrical impulses in your muscles, interactions between charges, mediated by electromagnetic fields, let you curl that finger around a pen and lift it. In doing so, a tiny imbalance of electric forces in your body overcomes the gravity of the Earth acting on the pen. No ceremony, no conflict, just rules adding up. Gravity has another peculiarity. It is always attractive. There are no negative masses to cancel positive ones. And it has infinite range. Every mass in the universe pulls on every other mass, however faintly. That reach makes it the dominant shaper of structure on the largest scales, galaxies, clusters, the cosmic web. Not because it is strong, but because it never shuts off and never reverses. If the universe has a tendency at large scales, it is simply this: matter curves space-time, and space-time curves the paths that matter can take. A different manager governs almost everything you actually feel. Electromagnetism is responsible for light, chemistry, electricity, magnetism, and almost every sensation you associate with solidity. It is what stops your hand when you press it against a wall. The atoms in your palm never literally touch the atoms in the paint. Their electron clouds repel one another. The closer they get, the steeper the energy cost. You experience that gradient as pressure. The same interaction carries signals in your nervous system. Voltage differences across cell membranes, ion flows through tiny gates, cascades of charged particles. All of that is electromagnetism at work. The thought, "I am sitting," is encoded in a pattern of electrical activity imposed on a physical brain held up by electromagnetic repulsion. At the particle level, this rule is mediated by photons, not just the visible light that reaches your eyes. Virtual photons, constantly being exchanged between charged particles. They are not little billiard balls flying back and forth, but quantized disturbances in the electromagnetic field. To the equations, they are a bookkeeping device that keeps the rule consistent. You never asked for photons to exist, yet everything from your heartbeat to the glow of your screen depends on their obedience. Deeper inside each atom sits the most intense of the four managers. The strong nuclear interaction is what keeps protons packed together in a nucleus, despite their mutual electrical repulsion. Stack several positively charged particles into a tiny volume and, by electromagnetism alone, they should fly apart. They do not. Something stronger is holding them. That something is the strong force, acting between quarks inside protons and neutrons. Its carriers are gluons, particles, that link quarks together in combinations that cannot be isolated. Try to pull two quarks apart, and you do not get a free quark. You get more quarks, more bound states. The field responds by creating new matter rather than allowing the rule to be violated. In everyday terms, without the strong interaction, your body would not be a body. Every nucleus in every atom would disintegrate into a thin haze of individual protons and neutrons, and those would break further into a spray of quarks rushing away from one another. No solid matter, no chemistry, no chair. This manager works at a very short range, roughly the size of an atomic nucleus. It ignores you at macroscopic distances. It does not care about your center of mass or your orbital period. It only cares about color charge, a quantum label that belongs to quarks and gluons. It enforces its rule ruthlessly in that tiny domain and remains indifferent to everything else. Finally, there is the quietest of the four. But without it, the universe would be a very different place. The weak nuclear interaction is responsible for certain kinds of radioactive decay and for the nuclear reactions that power the sunday. It changes the identity of particles. A neutron can turn into a proton, an electron, and an antineutrino via the weak interaction. A proton in the core of the sun can, through a chain of weak processes, eventually contribute to the fusion of hydrogen into helium, releasing energy as light. The weak force is short-ranged and, in human terms, slow. It is mediated by heavy W and Z bosons. Their mass chokes off the range of the interaction, limiting it to subatomic distances. You do not feel the weak force in the way you feel gravity. You witness its effects in the steady ticking of a Geiger counter, the lifespan of certain unstable elements. The age of the sunday, neutrinos, nearly massless particles that interact only via the weak force and gravity, stream through your body in unimaginable numbers every second. Mostly from nuclear reactions in the sunday, they pass through you, through the Earth, without a trace. Because the weak interaction is so selective and rare. 4 managers, 4 domains. They do not blend in our everyday experience. Sitting on a chair, you feel only the balance between 2 of them. Gravity pulling you down, electromagnetism pushing you up. Inside you, the strong and weak are working invisibly, setting the stability of your atoms and the mix of elements in your blood. You are a junction point of 4 rulebooks that do not know you exist. It is tempting to imagine them as characters in a story, each with a personality. Gravity, solemn and patient. Electromagnetism, vivid and talkative. The strong force, intense and possessive. The weak force, subtle and transformative. But they have no intentions. They have coupling constants. Still, even at this level, the universe hints at a deeper economy. Electromagnetism and the weak interaction, for example, are not truly separate in the hot, early universe. At very high energies, they merge into a single electroweak interaction. Only as the universe cools and the Higgs field settles into a particular configuration do they split into the electromagnetic and weak forces we see today. From that point of view, the 4 managers are not fundamental. They are the low-temperature faces of something more unified. Gravity complicates this picture. Unlike the other 3, it is not part of the standard model. It is described by general relativity, a classical theory of space-time curvature, rather than by a quantum field theory with gauge bosons we have detected. On paper, you can imagine gravity having a quantum carrier too, the graviton, a hypothetical spin 2 particle. If gravitons exist, they orchestrate the gravitational interaction in the same way photons, gluons, and Z bosons orchestrate their respective forces. But we have not observed individual gravitons. They hide behind the weakness and large-scale smoothness of gravity. This mismatch, 3 forces in one framework, one in another, is one of the central tensions in modern physics. 2 different rulebooks apparently describing the same universe. Some ideas try to soften that tension by changing the stage itself. If gravity seems so weak compared to the other 3, perhaps it is not inherently feeble. Perhaps it is diluted. If space-time has more than 3 spatial dimensions, and if the other forces are confined to a 3-dimensional brain, while gravity can spread through the extra dimensions, its apparent weakness in our world could be a projection effect. From our point of view, that would look like gravity leaking sideways into directions we cannot move in. These are speculative frameworks, not established facts. But they share a common feature. They do not introduce a supervisor. They introduce more structure, more geometry, more ways for fields to extend and wrap and blend. Imagine, again, the person sitting on a chair. Zoom in past the level of skin and clothing. At the microscopic scale, atoms in the chair lattice vibrate around equilibrium positions set by electromagnetic forces. At the boundary, electron clouds from the chair and the body press against one another. At the same time, every proton in every atom of the body and the chair is pulling on every other proton via gravity, in a collective sum that anchors both to the planet. Deep in the nuclei, the strong interaction holds protons and neutrons together. In a few of those nuclei, a neutron will, eventually, undergo a weak decay, turning into a proton and emitting an electron and an antineutrino. In the sun, far away, an unending network of weak and strong interactions is fusing hydrogen into helium, bathing the room in a faint leakage of starlight. None of these processes is optional. None of them pauses if you stop thinking about them. None of them checks whether a distant galaxy, or a deity, or a human story approves. The picture that emerges is not of 4 gods in competition, but of 4 non-negotiable ways that reality permits change. A mass curves space-time. A charge sources an electromagnetic field. A color charge binds into hadrons. A flavor changes through weak processes. From those stark lines, everything else is downstream. Chairs, hands, magnets, stars, chemical bonds, detectors, the muon ring at Fermilab, the neurons in your brain. The phrase fundamental force can mislead. It sounds like a push, a shove, an agent. What we really see are patterns in how configurations evolve. Allowed transitions and forbidden ones, stable combinations and unstable ones, symmetries that hold and symmetries that break. The universe does not care what we call these patterns. It does not label them. It only enforces them. And yet, even here, in this tidy list of 4 interactions, the same unease that surrounds the muon experiment appears again. Why 4? Why this particular hierarchy of strengths and ranges? Why these coupling constants and not others? Ask those questions, and the 4 managers begin to look less like ultimate rules and more like low-level settings, frozen in from an earlier, hotter time when the universe was simpler and more unified. The person on the chair is balanced at the intersection of those settings. The fact that their body does not collapse, does not fall through the seat, does not fly apart into a spray of particles, is not evidence that someone is watching over them. It is evidence that the rules, as they are enough. A universe that balances 4 separate rulebooks invites another question. Are they really separate? Or are we just standing too close to see the pattern that stitches them together? London, 1864. A hot, heavy summer, air thick with coal smoke and horse sweat, and the faint metallic tang that clings to a city before a storm. James Clerk Maxwell, 33 years old, works in an office at King's College London. The room is dim. Paper, chalk, ink, equations creeping across pages that will outlive him by centuries. At some point, he opens a window. Outside, clouds are gathering. The first gust of cooler air cuts into the room, and with it comes a sharp, slightly sweet smell. Ozone, the signature of charged air. Molecules torn apart and reassembled by electric discharges in the sky. It is an ordinary moment. A human body, a window, a storm. Yet the same rules that are about to send lightning cracking through those clouds are also sitting quietly in Maxwell's notebooks. For most people in that city, electricity and magnetism are separate curiosities. Static electricity. The way a rubbed glass rod can attract scraps of paper. The way a comb crackles through dry hair. The little shocks from a doorknob in winter. Magnetism. The pull of a lodestone on iron filings, the compass needle aligning with Earth's field. The invisible influence that can turn a piece of iron into something that tugs on other iron. Different tricks, different demonstrations, different lecture props. The idea that they might be one phenomenon under different disguises is not obvious. It is not emotionally satisfying. It is just where the equations keep pointing when you stare at them long enough. Maxwell does that staring. Take a simple experiment. You rub a glass rod on a wool coat and bring it near a thin stream of water from a tap. The water bends. Something in the rod is influencing molecules in the stream at a distance. If you move a magnet near a coil of wire, you induce a current. If you run a current through a wire, a compass placed nearby will twist. One effect appears to mirror the other. Electric changes create magnetic responses. Magnetic changes create electric responses. Faraday had already mapped out many of these relationships experimentally. He spoke in terms of lines of force, mental images of invisible strands curling around magnets and charges. To a mathematician like Maxwell, those lines look like something else. Field lines, the geometry of a rule. In his office, with the storm pressing against the glass, he begins to encode those relationships in a new way. Not as separate tricks, but as a set of coupled equations. One describes how electric charges create electric fields. One describes how magnetic poles, or more precisely currents, create magnetic fields. Another describes how changing magnetic fields induce electric fields. And then, crucially, a term that says changing electric fields induce magnetic fields as well. That last step is the quiet revolution. If a changing magnetic field can make an electric field, and a changing electric field can make a magnetic field, then a disturbance in one can feed the other, and back again. A self-sustaining oscillation. Once started, it can propagate through empty space. From that logic, a new kind of wave falls out of the chalk. Maxwell calculates the speed such a wave would have, using known electrical and magnetic constants measured in the laboratory. The number he gets is close to 300,000 kilometers per second. That speed is familiar. It is the measured speed of light. The implication is unsettling in its simplicity. The glow from the storm clouds, the beam from a candle, the light slipping through his window, all of it could be manifestations of these electromagnetic vibrations, fields disturbing one another in a vacuum. The storm outside and the equations inside are, in that sense, the same event described at two different resolutions. Electricity and magnetism become electromagnetism. Two forces merge into one field. Notice what has happened here. At the level we care about. No new deity steps in to explain the connection. No supervising intelligence is required to coordinate electricity with magnetism. The unification emerges directly from insisting on internal consistency. If the world allows certain relations between charges, currents, and fields, it is boxed into allowing others. Maxwell is not dictating to nature how it must behave. He is discovering how tight the constraints already are. Open a window in a room where someone is working with that kind of mathematics, and you are looking at a transition point. Before, people thought in terms of separate mechanisms. Static attraction, lightning, magnets, currents. After, those are all different aspects of one rule operating in different contexts. The smell of ozone hints at lightning channels forming overhead. Regions where electric fields in the clouds have become strong enough to tear electrons away from atoms, creating conducting paths for enormous discharges. The same equations that describe those fields also describe radio waves and the light from the sun and the signal moving through the fiber that might one day carry a copy of Maxwell's work. One rule, indifferent to scale. When you switch on a lamp today, you are not thinking about field tensors or boundary conditions. You are just filling a room with light. But what floods in is an electromagnetic wave, crossing space at that same speed Maxwell calculated from constants on the page. The chair you sit on, the device you watch videos on, the Wi-Fi signal carrying them, the electric grid feeding your home, all of that is a cascade of technologies that only works because the same equations apply everywhere, reliably, without negotiation. Between Maxwell and us, there is a straight line of consequences: telegraphy, radio, radar, X-rays, lasers, MRI machines, satellite communications. Each of these is an exploitation of the same structure. Different frequency ranges, different engineering, one underlying rule. You can treat that as a triumph of human ingenuity, or you can see something slightly colder hiding underneath. A universe that never once had to improvise to make any of this possible. The waves were always allowed. In the 19th century, before relativity and quantum mechanics, many physicists imagined these electromagnetic waves propagating through a medium they called the luminiferous ether. Space, they thought, could not be empty. There must be something to wiggle. Later experiments looking for that ether, like Michelson and Morley's interferometer work in the 1,880 seconds, failed to find it. The speed of light remained the same in all directions. The ether quietly vanished from serious physics. The waves stayed. Again, the pattern repeats. An extra story falls away, the core rule remains. The universe tolerates fewer decorations than we would like. Maxwell's work has another effect. It shifts how force itself is understood. Instead of thinking of objects pulling or pushing at a distance across a void, you think of fields filling space, with objects responding locally to conditions in their neighborhood. A charge feels the electric and magnetic field where it is. A current feels the field where it flows. The action does not leap invisibly across the gap. It travels through the field with a finite speed, constrained by the structure of the equations. That view will later mesh naturally with Einstein's way of seeing gravity, not as a mysterious pull between distant planets, but as the curvature of space-time affecting the paths that matter can take. Different mathematics, different domain, same instinct. Replace distant reaches with local rules. You can sense the direction. Bit by bit, the picture of a universe run by specific interventions gives way to one run by universal relations. Instead of, who did this? You get what had to happen here, given everything else. In that light, the detail about Maxwell's window is not just historical color. It is a metaphor for something the laws themselves are doing. They open a window between seemingly separate territories. Magnetism stops being its own thing. It becomes electricity in motion. Light stops being an independent substance. It becomes the result of oscillating electric and magnetic fields. What feel like different experiences for us: a static shock, a compass turning, a beam of light. The warning smell before a storm become different faces of the same underlying geometry. The universe shrinks its list of ingredients. You can push that idea into more abstract territory. Behind Maxwell's equations lie symmetries, invariances under certain transformations. Rotate your coordinate axes, shift your origin, and the form of the equations stays the same. Later, gauge symmetry's redundancies in how we label fields will take center stage. Change the internal phase of a field in a particular way, and the physics does not change, as long as you also adjust the potentials appropriately. From that perspective, forces are not arbitrary. They are the price reality pays to maintain deeper symmetries. It is a strange, impersonal logic. There is no preference here for our comfort. There is only a requirement. If the universe respects certain symmetries, then certain fields and interactions must exist. The step from two forces to one field is our first concrete hint that the four managers are not fundamental. It shows how much redundancy there might be in our language. What we call electric and what we call magnetic are labels we invented for convenience. Nature is free to ignore those boundaries. That indifference cuts both ways. It allows us to build a coherent mathematical picture where the smell of ozone before a storm and the light from a distant galaxy fall under the same rule. It also quietly removes one more place where we might have imagined an external organizer. If lightning and lamplight and sunlight are all consequences of the same field vibrating according to the same equations, where is there room for a separate hand deciding event by event? You can still imagine such a hand, if you want. You can picture a supervisor who chose the equations, who fixed the values of the constants, who set the initial conditions, but Maxwell's unification drains content from any idea of ongoing management. Once the rule exists, it runs on its own. A storm front moves in over a city. Charge builds up in the clouds and the ground. Electric fields grow. When they exceed a certain threshold, breakdown occurs, channels form, current surges, light and radio waves race outward. The process is complex, turbulent, sensitive to tiny perturbations. But at every point, the fields obey the same local equations that Maxwell wrote down. The person at the window either notices or doesn't. The universe does not adjust either way. Later chapters in physics will make this even more extreme, merging weak and electromagnetic forces into an electroweak whole, speculating about grand unification, string theories, Browns. But this is where the trend first becomes unmistakable. Separate phenomena, unified description. Multiple forces, single field. Multiple stories, one set of constraints underneath. You can close the window again. The smell of ozone will fade. The storm will move on. The city will dry. Maxwell will die at 48, his body following biochemical rules he never wrote down. The equations will stay. They will sit on shelves and in archives and eventually on screens, and generators and antennas and processors will be built around them. People will learn to rely on their consistency the way they rely on gravity. Behind all of that is a simple, unsettling lesson. The more deeply we look into what we once thought were separate domains of nature, the more we find that they were never truly separate. We divided them because of how we experience them. The universe binds them because of how they must behave. And if two forces could turn out to be faces of one field, the question quietly deepens. How much of what we call many is just one rule, seen from too close? If separate forces can share a single face, the next question is simple and unnerving. What happens when we look so closely that force itself dissolves into something stranger? A lakeshore in New York, mid-20th century. Cold air, grey water, small wind-driven waves rolling toward a stone edge. Richard Feynman, young but already famous for a certain restless clarity, sits near Lake Cayuga while teaching at Cornell. Students see a charismatic lecturer, a fast mind, a man who jokes his way through blackboards. Out here, alone with the water, he is doing something quieter. He is watching ripples. A wavefront moves in from the middle of the lake. It hits a rock. Part of it reflects. Part of it bends around. Different paths for the same disturbance. At any point near the shore, the water's motion is the sum of all those contributions, adding and cancelling. To anyone else, this is just weather. To him, it is a sketch of how the universe might work at the smallest scales. Classical physics, the physics of Maxwell and Newton, describes particles following definite paths under definite forces. You specify starting positions and velocities, and the equations tell you where everything goes. Feynman is thinking about something more radical. What if, on the quantum scale, a particle does not follow one path, but every path it is allowed to take, all at once? What if the apparent trajectory we see is just the net result of an underlying sum over possibilities, like the pattern of waves on the lake? Out of that thought comes a new way of doing quantum mechanics, the path integral formulation. Instead of focusing on abstract wave functions evolving in time, you imagine every conceivable route a particle can take between 2 points. You assign each route a complex weight. and amplitude. Then you add them all. Where the contributions interfere constructively, you get a high probability. Where they cancel, you get almost none. No supervisor selects one path. The rules assign weights. The rest is arithmetic. That reformulation turns out to be more than a different language. It gives a natural way to talk about interactions. In a field theory, what we call a force is really an exchange of quanta. Charged particles interact by emitting and absorbing photons. Quarks interact by exchanging gluons. Particles subject to the weak interaction exchange W and Z bosons. The path integral picture captures this as a proliferation of possible histories. In some histories, an electron moves in a straight line. In others, it emits a photon that later gets reabsorbed. In still others, it emits a photon that briefly materializes into a particle-antiparticle pair before recombining. You can draw these possibilities as diagrams, little stick figures of particles joining and splitting. Each diagram is not a literal story of what really happened. It is a term in an expansion. You can think of them as bookkeeping devices for certain integrals, a visual shorthand for algebra, but their effect is real. When you add up their contributions, you get numbers that match experiments to astonishing precision. There is a catch. Many of the particles in those diagrams are not observable as free on-shell objects. They do not show up as spikes in detectors. They exist only as internal lines in the calculation. Physicists call them virtual particles. You could just as well call them ghosts of the rules. They are not ghosts in a mystical sense. They are artifacts of the way the field responds locally to disturbances. But the name captures something about their status in our picture. They are not part of the cast we can directly see. They are the invisible messengers that keep the conservation laws intact. Feynman's quantum electrodynamics, the theory that describes how light and matter interact, turns this mathematical machinery into a predictive engine. It calculates the tiny shifts in the electron's magnetic moment caused by its constant dance with the electromagnetic field. It accounts for subtle shifts in the energy levels of hydrogen atoms. It explains scattering patterns in accelerators. The agreement with experiment, when you plug in the numbers, is almost unnerving. Tiny corrections, involving many layers of virtual processes, produce results that match measurements out to many decimal places. For a human theory written on paper, that level of accuracy feels unreasonable. Again, the lesson is not that we are clever. It is that the constraints the universe obeys are so strict that, once we align with them, the room for error collapses. One of the clearest windows into this ghostly activity appears a little farther away. In the work of a Dutch physicist named Hendrik Casimir, also in the late 1940s. Imagine two uncharged, perfectly conducting metal plates facing each other in otherwise empty space. Place them extremely close together, separated by a distance small enough that only a limited set of electromagnetic wave modes can fit between them. Outside the plates, the vacuum can support more modes. Inside, fewer. If the quantum vacuum were truly empty, nothing should happen. But in quantum field theory, even the ground state is active. Fields fluctuate. Virtual photons wink in and out of existence, constrained by the uncertainty relations. In such a picture, modifying the allowed mode structure between the plates changes the vacuum energy there compared to outside. The result is a tiny net pressure pushing the plates together. You do not need to believe in virtual particles as literal little balls bouncing around to make sense of this. You only need to accept that the electromagnetic field has a spectrum of allowed modes, and that boundary conditions can reshape that spectrum. The force follows from the change in energy. The Casimir effect takes an idea that sounds like an abstraction, vacuum fluctuations, and drags it halfway into the lab. It is not dramatic, no thunderclap, just an almost imperceptible attraction between polished surfaces, measurable only with careful isolation and sensitive equipment. Still, the message is stark. Even what we call nothing is governed by rules rich enough to produce measurable consequences when you slightly change the conditions. No watchful presence is required to push the plates. No hidden intention. The force arises from a difference between two allowed configurations. The same mathematical structure that gives you the electromagnetic force between charged particles also gives you this pressure between neutral plates. Different diagrams, same field, same basic constraint. The universe prefers some arrangements over others, according to a fixed recipe. Once that becomes clear for electromagnetism, it is tempting to extend the logic. The strong interaction can be described with a similar, though more complicated, quantum field theory. The carriers there are gluons, which, unlike photons, interact with one another because they carry the very charge they mediate, a property called color charge. This self-interaction is part of why quarks are confined inside hadrons and never seen in isolation. The weak interaction also fits into the framework, with massive W and Z bosons taking the role of messengers. Their mass limits the range of the weak force, making certain processes rare and slow on human scales. But the underlying mathematics is still that of gauge fields and path integrals. Step back, and the pattern sharpens. 3 of the 4 managers can be written in a common language. They are gauge theories based on symmetries of abstract spaces. Their forces emerge from requiring that the physics looks the same when you make certain local changes to how you label the fields. The particles are excitations of those fields. The virtual quanta are internal ripples that never quite break free. It is not that someone decided to send a gluon or a photon between 2 particles. It is that the demand for local symmetry forces the existence of fields, and those fields enforce specific couplings. In this landscape, the figure by Lake Cayuga is less a romantic image and more a hint of what our experience really is. A macroscopic wave pattern, rising out of an uncountable sum of microscopic histories, none of which is chosen by hand. Then there is gravity. Gravity is still written, in our best theory, as curvature of spacetime rather than as a quantum field with exchanged quanta. General relativity describes it with great elegance on large scales, from planet orbits to black hole mergers to the expansion of the cosmos. But when you try to apply the same quantization machinery that works so well for electromagnetism and the nuclear forces, things go bad quickly. Naive attempts to treat gravity as just another field produce integrals that blow up uncontrollably at high energies. The theory becomes non-renormalizable, meaning its infinities cannot be tamed with the familiar tricks. There are ways to soften this. You can treat general relativity as an effective field theory, valid up to some extremely high energy scale, beyond which new physics must appear. You can explore approaches like loop quantum gravity. You can embed gravity in more comprehensive frameworks, which will appear later in this story. But right here, at the level of Feynman diagrams and ghostly exchanges, gravity is the holdout. We can write down a graviton, a hypothetical quantum of the gravitational field, with spin 2 and no mass. We can imagine diagrams where matter exchanges gravitons in the same way it exchanges photons. We can even calculate certain low-energy processes consistently. Yet the full, ultraviolet complete quantum theory of gravity remains out of reach. So we live with 2 rulebooks. On one side, a quantum world, where forces are encoded as exchanges of virtual particles, where vacuum fluctuations push metal plates together, where path integrals over countless histories give precise scattering amplitudes. On the other, a geometric world where mass and energy curve spacetime, where that curvature tells matter how to move, where light follows null geodesics through a dynamical metric. So far, the universe seems comfortable with this split. For most practical problems, you can choose one description or the other and be fine. Quantum field theory for particle physics and condensed matter. General relativity for cosmology and gravitating bodies. We are the ones who are uncomfortable. Our instinct is to expect a single coherent manual, a unified narrative where every force is just a facet of one deeper entity. The failure to quantize gravity fully feels, to us, like something is missing. From the universe's point of view, there is only this. In each regime, where we can test it, behavior is consistent with some internally tight set of rules. Where those regimes overlap slightly, the rules match well enough that we can translate between descriptions. The man by the lake the ghost particles in his equations, the plates in Casimir's thought experiment, the curvature in Einstein's field equations. All of these are our attempts to write down what those rules might be. None of them require that someone be out there watching, correcting, intervening when an amplitude misbehaves. In the wave picture Feynman likes, every path contributes. Histories where a photon is emitted, where it is not. Where a pair appears and annihilates, where plates sit close together or far apart, all of them are weighed according to the same action, the same stationary principle. The ones that dominate are not chosen because they are meaningful or elegant. They dominate because the phases line up. Interference, not intention. Standing at the edge of Lake Cayuga, if you fix your eyes on a single point where waves meet, you see peaks and troughs that feel local and immediate. Shift focus, and you see they are the consequence of reflections from distant shores, of wind patterns across the surface, of boat wakes and currents. The spot in front of you is just where all those influences add. Our position in the universe is like that point. Our laws are our attempt to describe the patterns in the ripples. Ghost particles, path integrals, vacuum pressures, curved metrics. These are the languages we have found so far. They all tell a similar story. Reality evolves by rules that care about symmetries and actions, not about watchers or managers. And if that is true at the level of a single electron's trajectory, it becomes harder to insist that somewhere above it all, a separate will is adjusting the paths by hand. If every interaction we see is already the result of rules, there is a quieter question hiding underneath them. Were there ever fewer rules than this? Follow the universe backward in time, not with imagination first, but with the equations that currently survive our tests. As the cosmos contracts in our mental rewind, galaxies blend into a uniform glow. Stars, atoms, even nuclei smear into a hot plasma. Temperature climbs, densities rise. At some point, our usual descriptions begin to blur, then fracture. That boundary has a name: the Planck era. Planck time is a scale where quantum mechanics and gravity become equally loud. In familiar units, it is roughly 10 to the minus 43 seconds after the Big Bang. At that age, any attempt to describe space-time as a smooth fabric becomes suspect. Quantum fluctuations in the geometry itself are expected to be violent. The density would approach what is called the Planck density, where the very distinction between space and matter threatens to disappear. We do not have a complete theory for this regime. What we have are hints. Candidates like quantum gravity and supergravity, sketches of how a unified description might behave if it truly existed. What matters for our story is what comes next. Slightly after this Planck time, as the universe continues to expand and cool, many cosmological models introduce a brief period called the Grand Unification Epoch. During that window, somewhere between about 10 to the minus 43 and 10 to the minus 36 seconds after the Big Bang, 3 of the 4 known interactions are thought to have merged into a single entity, sometimes called the electronuclear force. Gravity has already peeled away. Strong, weak, and electromagnetic interactions are, in this picture, different aspects of one rule. The temperatures involved are hard to relate to anything human. If you translate the relevant energy scale into temperature, you get numbers above 10 to the 27 Kelvin. Expressed as a characteristic energy, many grand unified theories place this unification around 10 to the 15 giga-electron volts, give or take an order of magnitude. This is about 10 to the 12 times higher than the energies reachable at machines like the Large Hadron Collider, whose collisions sit in the range of hundreds to thousands of giga-electron volts. At those early moments, distinctions that feel obvious to us simply do not exist. You cannot meaningfully talk about a strong force separate from an electroweak one, just as you cannot distinguish heads from tails on a coin spinning too fast to resolve. Symmetries that are broken today are intact. Quantum numbers that now matter deeply like electric charge as we usually measure it. Or the difference between quarks and leptons may not yet have the same status. The universe is in a higher symmetry phase. It is less structured, not more. This kind of unification is not magic. It is a feature of how quantum field theories behave when you push them to higher energies. In the standard model, The strengths of the strong, weak, and electromagnetic interactions run with energy. Their effective coupling constants shift as you probe shorter distances. Plot those strengths as curves on a graph and extend them upward, and you see them drift toward one another. Many proposed grand unified theories make that convergence exact at a very high scale, around 10 to the 15 or 10 to the 16 giga-electron volts, depending on the model and assumptions. They meet at a point called the grand unification scale. Above that point, in those models, you do not have three separate gauge groups with three independent couplings. You have one larger symmetry group with a single coupling. The separate interactions are low-energy remnants of that larger structure, broken as the universe cooled. The superforce is not a fifth force layered on top of the others. It is their ancestor. Cooling is the only director in this story. As the universe expands, its temperature falls. At some critical threshold, the grand unified symmetry would have become unstable. The way a superheated liquid suddenly boils, or a cooling metal suddenly becomes magnetized. The unified force splits. The strong interaction detaches from the rest. Later, at lower energies, the electroweak force itself divides into the weak and electromagnetic interactions we know. The chronology is fuzzy around the edges, but a common picture places the separation of the strong force around 10 to the minus 36 seconds, and the later electroweak symmetry breaking, where the Higgs field settles into its non-zero value and particles acquire mass, around 10 to the minus 12 seconds after the Big Bang. No one flips a switch at those moments. There is no cosmic engineer toggling settings. The phase transitions are, in the mathematics, consequences of the potential energy shapes of fields and the cooling rate of the universe. Given the initial hot, dense state and the particular form of the underlying symmetries, these breakings are not events that might or might not happen depending on preference. They are built-in outcomes. This is where the idea of symmetry breaking becomes less abstract and more physical. Take water. At high temperatures, its molecules move freely, and the liquid looks the same in every direction. As you cool it below 0 degrees Celsius at normal pressure, ice forms. The crystal lattice picks specific directions in space. The system's behavior changes because the lower energy configuration in the new conditions has less symmetry. No one selects the orientation of each crystal face by hand. The laws allow many equivalent choices. The system chooses one through local fluctuations and then locks in. In cosmology, grand unification and electroweak breaking are imagined as similar transitions in more abstract spaces. Fields that once sat at symmetric peaks roll down into valleys. Different patches of the universe may roll in slightly different ways. Defects, domains, and relics could form, depending on the details. But through it all, there is no superposed intention guiding a preferred outcome. There is a field, a potential, and the cooling of space-time. The electroweak part of this story is the one we have the best grip on, because it has been developed into a precise theory and tested at accessible energies. In the late 1960s and early 1970s, Sheldon Glashow, Abdus Salam, and Steven Weinberg built a framework that unifies the weak and electromagnetic interactions into a single electroweak theory based on a combined gauge symmetry. At high energies, above a characteristic electroweak scale, the distinction between photon, W boson, and Z boson blurs. They are all massless carriers of one force. Below that scale, after the Higgs field acquires a non-zero vacuum expectation value, the symmetry breaks, and the W and Z become heavy, while the photon remains massless. In 1979, Glashow, Salam, and Weinberg shared the Nobel Prize in Physics for this work on unifying the weak and electromagnetic interactions. The characteristic energy associated with this electroweak breaking is around 246 giga-electron volts. The value of the Higgs field's vacuum expectation value in the Standard Model. In terms of cosmic history, the electroweak epoch is often placed in the range from roughly 10 to the minus 36 to 10 to the minus 12 seconds after the Big Bang, with the actual symmetry breaking occurring around 10 to the minus 12 seconds, as the temperature dropped below, on the order of 100 giga-electron volts. That epoch is a faint echo of the deeper unification hypothesized at the grand unification scale. Once you accept that electromagnetism and the weak force merge into one interaction at high energies, something we have strong experimental and theoretical support for the idea that the strong interaction might also join them at even higher energies stops feeling like a wild leap and starts feeling like a continuation of a pattern. The earlier superforce would then be a single gauge interaction, perhaps described by a larger symmetry group such as SU5 or SO10, whose spontaneous breaking leaves behind the three separate gauge groups of the standard model. We do not have direct experimental access to that scale. Grand unified theories predict phenomena like proton decay mediated by heavy X and Y bosons, with lifetimes so long, often estimated beyond 10 to the 34 years, that even huge detectors have not yet seen an event. They sketch possible mechanisms for generating tiny neutrino masses, and for setting the balance between matter and antimatter. They tie together particle properties that, in the standard model alone, look arbitrary, but none of these sketches has been confirmed in full. The superforce remains, for now, a carefully structured speculation. Even so, for the question we are following, the speculative edges are not the main point. The important feature is the direction that all of these ideas lean toward. They describe a universe where, the hotter and denser you go, the fewer independent interactions you need to posit. Gravity ties into quantum descriptions near the Planck scale, at least in candidate frameworks. The strong, weak, and electromagnetic forces unify around the grand unification scale in many models. The weak and electromagnetic forces are already known to share a common electroweak origin. The multiplicity we see at human energies looks, from that vantage, like differentiation, not design. The persona of a superforce can be misleading. It sounds like a cosmic overseer. In physics language, it is more austere, a single symmetry group with a single coupling, operating at scales we no longer inhabit. When the universe cooled past certain thresholds, that symmetry could not remain unbroken. The lowest energy configuration changed, and with it, the way particles interacted. The superforce fractured into specialized roles, the way a homogeneous fluid fractures into distinct phases as you cross different lines on a phase diagram. From inside the late-time universe, it is natural to give those roles names: gravity, electromagnetism, strong, weak. It is natural to tell stories where they are separate actors. From the perspective of the early universe, they are just different limits of one structure. What looks to us like a committee of four managers is, in that sense, the fossil of a single rule stretched by cooling into different behaviors. And the engine that drives every step of that unfolding from Planck-era chaos through a grand unified phase into the electroweak epoch and beyond is not a sequence of decisions. It is expansion, it is redshift, it is the steady draining of temperature from a universe that began unimaginably hot and has been cooling ever since, forced by its own geometry. If you imagine rewinding that cooling until all four forces blur again, the thought is not comforting. You lose electromagnetism as a separate thing. You lose the stability of nuclei as you know them. You lose chemistry, stars, chairs, and brains. What remains is not a designer leaning over a control panel. It is a simpler rulebook, thinner and more symmetrical, capable of generating complexity later as it fractures. The era of the superforce, whether or not we ever pin down its exact details, carries a particular implication. The further back you go, the less room there is for separate kinds of intervention. There is only the tightening of constraints, the merging of interactions, and the silent fact that, once the initial conditions and laws are in place, the story of breaking and differentiation does not need anyone to supervise it. If the early universe once ran on a single superforce, there is a more radical possibility hiding behind it. Maybe even that force is not fundamental, just the low-energy shadow of something thinner and stranger. In the late 1960s, the trail does not start with gravity. It starts with the strong nuclear force and a puzzle about how hadrons scatter. The data coming out of particle accelerators showed families of particles lying on smooth reggae trajectories, their spins and masses marching in an eerie pattern. Physicists wanted an equation that could capture those patterns without committing to the usual quantum field theory language. In 1968, Gabriele Veneziano found one, the Euler beta function, repurposed as a scattering amplitude between mesons, had all the right properties of duality and symmetry. At first, it was just a clever formula. Then Yoichiro Nambu, Holger Bech-Nielsen, and Leonard Susskind noticed something unsettling. The mathematical structure of the Veneziano amplitude looked exactly like the spectrum of a vibrating string. If you treat the excitations in the formula as modes of a one-dimensional object, a string, you naturally generate an infinite tower of states whose masses and spins resemble the hadronic reggae trajectories. The dual resonance model could be read as the physics of an extended object, not a point. So a speculative picture emerged. Perhaps what we call particles are just different notes on tiny strings. Different vibrational patterns give different masses and spins. Instead of point-like quarks exchanging gluons, one-dimensional strands flicker and interact. For a few intense years, string-like models of the strong force attracted hundreds of theorists. They promised a unified description of hadronic scattering, a graceful alternative to the messy infinities of quantum field theory. But the enthusiasm hid serious problems. The simplest bosonic string model predicted a particle with spin 2 and 0 mass in its spectrum. For a theory meant to describe the strong force between hadrons, which is short-ranged and does not involve a long-range spin 2 field, this was a glaring mismatch. The model also lived naturally in 26 spacetime dimensions, not 4. It had a tachyon, a mode with imaginary mass indicating an instability. And as quantum chromodynamics crystallized in the early 1970s, a gauge theory of quarks and gluons that fit the data far better, the string picture began to look like a beautiful wrong turn. By around 1973, many in the community had moved on. The dual resonance model, once a leading candidate for the strong interaction, was widely regarded as dead. Quantum chromodynamics, with its asymptotic freedom and confinement, took center stage. The phrase string theory faded into the background textbooks as a historical curiosity. For most working particle physicists, the idea that tiny strings were fundamental simply stopped being useful. Yet in the same features that made the model a misfit for the strong force, a few people saw something else. That massless spin 2 excitation, so awkward in a hadronic theory, looked suspiciously like the graviton, the hypothetical quantum of gravity, in a future quantum theory of spacetime. In 1974, Joel Scherk and John Schwartz proposed taking that hint seriously. Reinterpret the string not as a model of the strong interaction, but as a framework that automatically includes gravity and might unify it with the other forces. Recasting the theory in that way required a conceptual flip. Instead of trying to match string modes to known hadrons at accessible energies, you imagine the fundamental strings living at scales near the Planck length, far beyond any current experiment. The spin 2 mode becomes the graviton. Other vibrational patterns correspond to gauge bosons and matter fields. The awkward extra dimensions are no longer mistakes. They become part of the geometry the strings move through, perhaps compactified into shapes too small to see. For almost everyone else, this was too speculative, too far removed from data. Through the mid-70s and into the early 80s, Scherk and Schwartz, and a small group of others, kept working on these ideas in relative isolation. They developed superstring versions of the theory, adding supersymmetry to tame some of the instabilities. They explored different ways to curl up the extra dimensions. They tried to see whether the known gauge groups of particle physics could arise naturally on the world sheet of a string. From the outside, this looked like devotion to a failed model, a kind of theoretical stubbornness. Inside the equations, something more impersonal was happening. The structure of the string spectrum kept insisting on gravitational degrees of freedom. The consistency conditions kept pointing to specific space-time dimensions. Anomalies, subtle inconsistencies that can render a quantum theory meaningless, showed up in most naive constructions and had to be cancelled with care. This is where a particular technical discovery, made in 1984, matters. Michael Green and John Schwartz found that in a 10-dimensional superstring theory of a certain type, with a specific gauge group, quantum anomalies that would normally break gauge and gravitational symmetries could cancel out precisely. This Green-Schwartz mechanism kicked off what is often called the first superstring revolution. Suddenly, string theory looked like a mathematically consistent framework that naturally included gravity and gauge interactions in one package. The timing is not the point. The logic is. Anomaly cancellation is not an aesthetic preference. It is a requirement for any quantum theory with gauge symmetries to make sense. Left uncancelled, anomalies lead to violations of charge conservation and other disasters. In ordinary quantum field theories, the condition that anomalies vanish places strict constraints on particle content. In the string setting, the Green-Schwartz mechanism showed that certain string constructions automatically satisfy those constraints, while many others do not. So, the theory began to filter itself. Most naive combinations of strings and gauge fields simply fail the internal consistency checks. A few survive. Those few tend to share features. 10 dimensions. Specific gauge groups. Supersymmetry. You can push against that structure, trying to construct more general models, but the mathematics pushes back. Anomalies reappear. Infinities creep in. The rules are not negotiable. If you step back from the technical details and follow the arc, string theory's death and resurrection does not look like a story of human taste changing its mind. It looks like a sequence of increasingly strict constraints being discovered. The model was born when a certain kind of amplitude turned out to match data on hadrons. It died in that role when a better theory arrived and the mismatch became obvious. It re-emerged in a different role because features that were liabilities for hadronic physics, the spin-2 state, the high dimensionality line up disturbingly well with what any theory of quantum gravity seems to need. That does not make string theory true. It makes it hard to ignore. In its modern form, the picture is severe. Fundamental strings, or more generally, extended objects called brains, vibrate in a space-time with more dimensions than we directly perceive. Different vibrational modes correspond to different particle species. Interactions arise from strings splitting and joining, or from brains colliding and intersecting. The force of gravity is no longer an add-on. It is built into the spin-2 excitations of the closed strings. Gauge forces sit on open strings whose ends are tied to brains. Compactification, the curling up of extraspatial dimensions into tiny, intricate shapes, then determines much of the low-energy physics. Which particles exist, what their masses are, how strongly they interact. Change the shape, and you change the effective laws in the lower dimensional world. That dependence can feel like freedom, like an enormous landscape of possibilities. From another angle, it is just more structure. The dynamics of higher dimensional geometry constraining what can appear in the low-energy effective theories. At this point, the temptation is to dramatize, to turn string theory into a near-religious candidate for a theory of everything, or to dismiss it outright as an elaborate mathematical mirage. Both moves import expectations from outside the rules. What the equations actually offer is more modest and more disturbing. They sketch a framework where gravity and gauge forces arise from a single type of object. They enforce specific dimensions. They tightly restrict which combinations of fields and symmetries can coexist without contradiction. They give, in some regimes, concrete dualities and correspondences that match known physics. They have not yet produced a unique low-energy world that looks exactly like ours, with measured particle masses and couplings pinned down from first principles. They may never do that. In other words, string theory is a candidate for the deeper rulebook, but not yet an identified one. From the perspective of our question, the details of its eventual fate are almost secondary. What matters is that, as physicists pushed past the era of the superforce and tried to fold gravity into the same quantum schema, they did not find room for an arbitrary range of theories. They found that consistency itself is a narrow target. Many ideas fail not because they are inelegant, but because they simply cannot exist without breaking their own symmetries. String theory sits at that boundary, elaborate, constrained, and indifferent to what we would prefer. The resurrection is not a happy ending. It is a reminder that the universe seems to favor descriptions where fewer independent ingredients do more work. A spinning string that once pretended to be a hadron turns out to contain, almost against our wishes, the seed of a graviton. A misapplied model of the strong force becomes a natural arena for unification once we let go of the original story we told about it. You could say that the theory was rescued. Or you could notice something quieter. Left to itself, the mathematics kept pulling toward gravity, toward higher dimensions, toward unification. Human attention arrived late. When attention finally did arrive, it did what it always does. It split the picture into pieces it could name. The mathematics had hinted at unity. The human response was fragmentation. By the late 1980s, string theory had gone from an odd side project to a central obsession for many theorists. The Green-Schwarz result had opened a door. Here was a framework that seemed internally consistent, that contained gravity, that might unify all the forces in a single geometric language. For a certain kind of mind, this was intoxicating. There was a sense of standing near a coastline of something enormous, with fog lifting. And then, as the fog cleared a little, something embarrassing appeared. There was not one theory. There were 5. Type I, Type 2A, Type 2IB. Heterotic, so. Heterotic E, 8 times E8. Each of these superstring theories lived naturally in 10 spacetime dimensions. Each had supersymmetry. Each cancelled anomalies in its own way. Each had a different spectrum of allowed excitations, a different structure of allowed gauge groups, a different style of extended objects. They were not obviously equivalent. They did not collapse into one simple formulation. 5 is an awkward number when you are looking for one. If gravity and gauge forces are meant to be faces of a single underlying object, why should nature get to choose between 5 inequivalent fundamental descriptions? Why not one? Why not none? The neat story of a unique theory of everything began to fray. This is where the old parable of the blind men and the elephant began to haunt seminars. In that story, each blind person touches a different part of the animal. One feels the trunk and decides an elephant is like a snake. Another holds the leg and insists it is like a tree. A third grasps a tusk and concludes it is a spear. Each report is accurate about a fragment and wrong about the whole. None of them has enough information to say what an elephant is. String theorists in the late 1980s were, in a sense, those people. Each touch, each consistent theory described a complete, closed world with its own rules. A 10-dimensional cosmos with its own spectrum of strings and brains and interactions. No obvious way to step from one to the other. No proof that they were pieces of something larger. No proof that they were not. Viewed from the outside, the situation looked even worse. After the first wave of excitement, string theory's connection to experiment remained tenuous. The characteristic energy scale of the fundamental strings lived near the Planck scale, far beyond any collider dreams. Predictions that might distinguish one compactification from another were fuzzy, buried under layers of assumptions. Critics began to mutter that the theory risked drifting into the territory Wolfgang Pauli had once reserved for the worst ideas, not even wrong. That phrase is sharper than it looks. A wrong theory makes clear claims that can be tested and falsified. A framework that is too flexible, with too many adjustable choices, can always be tuned to accommodate what is already known, while failing to say anything definite about what comes next. 5 consistent string theories, each with an enormous number of possible ways to curl up extra dimensions, each capable in principle of producing different low-energy physics, look disturbingly like that kind of flexibility. From one angle, it was a triumph of mathematical consistency. Instead of countless sick models, here were a handful of robust ones. From another, it was a maze with no exit. Underneath the sociological noise, something quieter was at stake. If the universe is rule-based rather than supervised, you expect the rules to be tight. You expect that as you climb toward more fundamental descriptions, fewer options survive. The picture emerging in particle physics and cosmology fit that pattern. Separate forces, unifying at high energies. Symmetries enlarging. Distinct behaviors, becoming limits of a single structure. 5 disconnected string theories cut against that intuition. They made room, at least in appearance, for contingency at the very bottom. Perhaps, some thought, this is simply how it is. Perhaps the ultimate rules of reality do come in multiple versions, all internally consistent, all equally real in some higher sense. Perhaps our universe is just one branch of a much larger landscape of possibilities, selected by mechanisms we do not yet understand. In that view, the 5 theories are not a problem, but a hint that the space of consistent laws is wide and varied. That idea carries its own unease. It pushes any notion of necessity of things being the way they must be further out of reach. Inside offices and lecture halls, the technical questions were more specific. How exactly were these 5 theories related? Could one morph continuously into another if you tuned parameters, like water turning to steam? Did they share deep dualities, hidden equivalences, where a strong coupling in one description corresponds to a weak coupling in another? Was the multiplicity real? Or just a mirage created by working in limited corners of a bigger, still unknown framework? Hints began to accumulate. Certain calculations suggested that Type 2Aa and Type 2b might be related by a transformation that flips a compact dimension into its inverse size, a duality exchanging winding modes of strings with their vibrational modes. Other work showed relationships between the heterotic theories and Type 1 under different dualities. Strong, weak coupling dualities hinted that what looked like very different regimes of different theories could, in fact, be 2 views of the same underlying physics. The metaphor of the blind fortune tellers touching an elephant became more literal. Each theory, explored in its own perturbative regime, reported a different shape for the underlying object. One saw a certain set of strings and D-branes. Another saw different branes, different gauge groups. When analyzed in overlapping regions, their predictions began to line up in surprising ways. Quantities computed in one theory matched quantities in another, even though the calculations used completely different starting points. To the people doing that work, this felt both exhilarating and disorienting. Every time a connection was found, the sense grew that the 5 theories were not separate islands. They were coastal outlines of one unseen continent. But the continent itself remained hidden. There was no single, non-perturbative formulation that contained all 5 as limits. No master equation from which they could all be derived as different expansions. Just webs of equivalence, dualities stitching the edges together, without a clear picture of the interior. Viewed from our question's perspective, the situation is almost a caricature of how humans approach a rule-only universe. We encounter phenomena from one vantage point. We invent a theory. It works in some range. We encounter more data from a different angle. The old theory cracks. A new one appears. Sometimes the new replaces the old. Sometimes, as with the 5-string theories, they both survive as partial, overlapping descriptions of something more rigid and more indifferent than either. We are the ones who feel the discomfort of seeing 5 paths where we expected one. The underlying structure, whatever it is, does not register that discomfort. If it has many consistent faces, it simply has them. If it has one face that we keep mistaking for many, it simply waits to be seen. If there is only one structure beneath many faces, there is a particular kind of moment when the fog lifts and you see that you were standing on one thing the whole time. In the mid-1990s, that moment happened in an auditorium at the University of Southern California. Outside, Los Angeles light, palm trees, traffic. Inside, a room full of theorists with coffee cups and notebooks at a conference called Strings 95, held from March 13th to March 18th, 1995. They arrived carrying the discomfort from the previous decade. 5 distinct superstring theories in 10 dimensions, plus an awkward cousin, 11-dimensional supergravity, a classical theory that looked too similar to be ignored and too different to be easily included. Edward Witten walked up to the blackboard that morning with a promise, half joking, half serious. 10 years earlier, he said, the field had faced the embarrassment of those 5 consistent string theories, plus that 11-dimensional cousin. By the end of the talk, he suggested, there would be just one big theory. On the surface, that is bravado. Underneath, it is a statement about rules. The work he presented there, later written up in a paper titled String Theory Dynamics in Various Dimensions, traced what happens when you push each of the known string theories into regimes where their usual perturbative descriptions fail. What emerges at strong coupling is not chaos, it is structure. For type 2a strings, that structure looks, at low energies, like 11-dimensional supergravity compactified on a circle. In plain terms, if you dial the interaction strength of type 2a string theory up instead of down, an extra dimension quietly appears in the effective description. The 10-dimensional string theory grows an 11th dimension in its strong coupling limit. The massless fields you would expect from 11-dimensional supergravity show up. The cousin that once sat off to the side becomes part of the family. Similar stories unfold for the heterotic theories and others. Dualities, relationships that map strong coupling in one theory to weak coupling in another, begin to stitch the 5 10-dimensional superstring theories together with 11-dimensional supergravity. What had looked like separate islands start to look like coastlines of one continent. The name given to that unseen continent is M-theory. In its most conservative formulation, M-theory is not a finished set of equations. It is a web of hints that there exists an 11-dimensional framework whose low energy limit is 11-dimensional supergravity, and whose various compactifications and limits reproduce all 5 consistent superstring theories in 10 dimensions. Type 2a becomes M-theory compactified on a circle. Heterotic E, 8 times E8, becomes M-theory compactified on an interval. Other corners match other choices of geometry and coupling. From this point of view, the 5 different superstring theories are not independent options the universe might choose from. They are different approximations to the same underlying object, valid in different ranges of parameters. Strong here, weak there. Large radius here, small radius there. What looked like many worlds is one world, sliced differently. The letter M in M-theory has been left deliberately ambiguous. Witten has suggested it could stand for magic, or mystery, or membrane. Different authors pick their favorite. The fact that the name is underdetermined, while the dimensionality is not 11, space-time dimensions at the fundamental level is its own kind of joke. Names float, the rules do not. One of the central features of M-theory is that strings are no longer the only fundamental extended objects. In addition to one-dimensional strings, the theory naturally includes higher-dimensional branes, 2-dimensional membranes, 5-dimensional 5-branes, and their higher and lower cousins. In general, a p-brane is an object with p spatial dimensions, sweeping out a p plus 1 dimensional world volume as it evolves. At low energies, M-theory is approximated by 11-dimensional supergravity, a field theory that includes solutions corresponding to these membranes and 5-branes. Compactifying one spatial dimension of that theory on a circle produces a 10-dimensional theory with strings. The string we started with shows up as a wrapped membrane, so the hierarchy flips again. In earlier string pictures, strings were fundamental, and branes were extended objects built from them. In the M-theory picture, an 11-dimensional membrane can give rise to a 10-dimensional string when one of its directions lies along a compact circle. What counts as basic depends on which description you use. The deeper point is that the consistency of the combined framework forces all of these objects to coexist and transform into one another under dualities. This is not a playground built for human satisfaction. It is a structure forced by the demand that quantum theories of gravity and gauge fields fit together without contradictions. Think about what had to line up for that morning in Los Angeles to make sense. The 5 superstring theories had to be anomaly-free in 10 dimensions. Their spectra had to fit certain supersymmetry constraints. The dualities between them, discovered piecemeal in the early 1990s, had to hold up under scrutiny. T-dualities relating large and small compactification radii, S-dualities relating strong and weak coupling, U-dualities, combining them in more intricate ways. 11-dimensional supergravity, written down years earlier as the maximal supersymmetric extension of general relativity, had to emerge in the right limits. No one designed these coincidences. They were uncovered step by step, each new match less likely to be an accident than the last. From a distance, M-theory looks like a clarification of the 5 blind fortune tellers and the elephant problem. The 5 10-dimensional string theories, plus their 11-dimensional cousin, are the partial touches. M-theory is the conjectured elephant, not fully seen but inferred from the way those touches line up. From our question's perspective, something else is happening. A universe that can be described by M-theory is not one where a supervisor picks a favorite string model. It is one where the space of consistent descriptions is itself constrained. If you write down quantum theories with certain symmetries and ask that they include gravity and remain free of anomalies, you are shepherded into a narrow region of theory space. In that region, what once looked like choices are revealed as coordinate changes. We do not know whether M-theory is the final word on that region. The theory remains incomplete in important ways. There is no single, universally accepted, non-perturbative definition that covers all backgrounds and all regimes. Many results are still derived indirectly, via dualities to better understood gauge theories, or via limits where supergravity is valid. But the pattern is clear enough to make one existential point. As theoretical physics advanced, the apparent menu of possible laws did not expand without bound. It repeatedly collapsed. Maxwell merged electricity with magnetism. The electroweak theory merged weak and electromagnetic forces. Grand unified models aimed to merge the strong force with them at higher energies. String theory tried to merge gravity with the rest. M-theory stepped in to merge the string theories themselves. At each step, what looked like separate systems became limits of a larger one. The mathematics did not open new doors of choice. It closed them. In that light, the 5 superstring theories and 11-dimensional supergravity were never 5 and 1. They were 6 ways of misseeing a single object. The discomfort physicists felt in the 1980s, the sense that the fundamental description of reality should not come in 5 inequivalent flavors, was not just aesthetic. It was a hunch about how ruthless consistency tends to be. M-theory is that hunch made precise enough to work with. Edward Witten did not stand at the board in Los Angeles and declare, "This proves there is one theory." He did something more modest and more unsettling. He laid out a chain of arguments suggesting that when you take the known string theories seriously at strong coupling and you follow their dualities wherever they lead, you keep landing in the same 11-dimensional structure. The talk did not settle everything. It shifted the default question. Instead of asking, which string theory does nature choose? The field began asking, which corner of M-theory are we living in? Instead of picturing the laws of physics as one of several equally fundamental options, you picture them as the low-energy byproduct of a particular compactification and vacuum in a single overarching framework. That shift has consequences for how we imagine choice at the deepest level. It is still possible, in many versions of the story, to talk about a landscape of possible vacua, different ways to curl up dimensions, different flux configurations, different low-energy effective theories. Some estimates put the number of distinct vacua in certain string-inspired settings at figures like 10 to the 500. Those numbers are fuzzy, model-dependent, and controversial. But the point they are trying to capture is straightforward. The same underlying rules may allow a vast variety of effective worlds. That variety can be taken as an invitation to anthropic reasoning, to multiverse pictures where our local laws are environmental accidents. Or it can be taken as another sign of how impersonal the underlying structure is. M-theory does not prioritize one vacuum over another. It does not single out one configuration as morally or aesthetically preferred. It only distinguishes between configurations that are allowed by its equations and those that are not. The selection, if it happens, is not a decision. It is a fact. From the vantage point of our everyday scale, this is all unreal abstraction. 11 dimensions. Brains. Dualities. Conferences in the 1990s. What does that have to do with a human life? with a person sitting at a desk at night thinking about whether the universe is supervised. This, the story of M-theory, is one of the clearest recent examples of how far you can go with rules alone. No experiment has ever given us a direct glimpse of an 11-dimensional membrane. No detector has measured a radius of an extra dimension that reveals itself only at Planckian energies. What we have instead are requirements. Anomalies must cancel. Unitarity must hold. Supersymmetry, if assumed, constrains representations. Dualities, if real, must be consistent in overlapping regimes. Those requirements, combined, drive the theoretical structure into a corner that looks like M-theory. You can walk away from that corner if you like. You can work on different approaches to quantum gravity or on more modest effective theories. The universe will not protest, but wherever you go, if you insist on consistency at all scales and on including gravity in the same quantum language as the other forces, you run into similar walls. Fields, symmetries, dimensions, and branes arrange themselves into limited patterns. From one angle, this is hopeful. It suggests that reality might, at bottom, be describable by a finite set of principles we could someday write down more completely. From another angle, it quietly removes another place where an ongoing, supervising agency would need to stand. If the deepest rules are that tight, what is left for a manager to do? They do not need to constantly adjust couplings. Those are fixed by the structure. They do not need to select a string theory. There is one framework with many corners. They do not need to patch up anomalies. Those either cancel automatically in allowed models or kill the theory before it is born. They do not need to uphold consistency. The mathematics upholds or destroys itself. We can still choose to imagine a chooser behind the rules. We can place intention at the level of why this structure and not another. That is a different kind of question. It does not show up in the equations. From inside the physics, what we see is an increasingly impersonal architecture. An auditorium in Los Angeles, chalk on a blackboard, a room full of people scribbling, frowning, erasing, a web of dualities tying 5 10-dimensional theories and an 11-dimensional cousin into a single, harder-to-escape picture, a name, M-theory. Pinned to that picture, like a label on an animal that still refuses to come entirely into view. And underneath it, the same quiet lesson that keeps repeating in different forms throughout this journey. The more of the structure we glimpse, the less room there seems to be for anything beyond rules. If the deeper structure keeps collapsing our options, there is one more boundary to test. Whether even our picture of space itself is more than it seems. Start not with strings, but with something heavier, a black hole. In classical general relativity, a black hole is simple. Take enough mass, compress it into a small enough region, and space-time curves so intensely that there is a surface, the event horizon, from which nothing, not even light, can escape. From outside, you see only mass, spin, charge. No hair, no details of what fell in. It is a clean, almost brutal object. And then you add thermodynamics. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that a black hole behaves like a thermodynamic system. It has a temperature. It radiates. It has an entropy, a measure of how many microscopic configurations correspond to the same macroscopic appearance. Entropy, in ordinary systems, scales with volume. Double the size of a gas-filled box, and the number of ways to arrange the molecules roughly squares. The more interior space, the more possible states. For a black hole, the entropy scales with area. More precisely, it is proportional to the area of the event horizon, measured in Planck units. Double the surface area of the horizon, and the entropy doubles. The interior volume can be enormous, even ill-defined, depending on how you slice space-time. The rule cares only about the boundary. That one fact refuses to fit a naive picture of reality. It whispers that the true number of degrees of freedom inside a region of spacetime is not set by how much room there is, but by the size of the boundary that encloses it. It hints that the most economical way to describe a gravitational system might be on a lower dimensional surface. Gerard, Hooft, and Leonard Susskind took that hint seriously. They proposed what is now called the holographic principle, a conjecture that a consistent theory of quantum gravity in some volume can be described by a theory without gravity defined on the boundary of that volume, with one fewer spatial dimension, like a hologram, where a two-dimensional surface encodes a three-dimensional image. It is an audacious idea, and for a while, it lived mostly as one. Then, in 1997, a quiet theoretical physicist named Juan Maldacena wrote down something more specific. He considered a particular space-time geometry, de Sitter space in 5 dimensions, with a 5-dimensional sphere attached to 10-dimensional arena that appears naturally in certain string constructions. In that bulk space-time, you can have gravity and strings propagating. On the boundary of that bulk, a 4-dimensional surface at infinity, you can define a quantum field theory without gravity, a conformal field theory with a specific amount of supersymmetry and a particular gauge group. The conjecture he put forward is now famous. The dynamics of the gravity plus strings theory in the bulk is exactly equivalent to the dynamics of that conformal field theory on the boundary. Not approximately, not poetically, exactly. If the duality holds as strongly as most evidence suggests, 2 descriptions, different dimensions, different languages, the same physics, a 5-dimensional gravitational world, complete with black holes and curved geometry, matched point for point to a 4-dimensional non-gravitational quantum field theory living on its boundary. What looks like a bulk spacetime with depth, distance, and interior can be reinterpreted as information living on a thinner surface. This is the holographic principle made concrete. You can picture it with something mundane. Imagine a can of soda. One way to describe it is to talk about the 3-dimensional liquid inside. Fluid flows, bubbles, eddies. Another way is to imagine that everything about the can is encoded in tiny dots on the 2-dimensional label, a densely printed code that, if decoded, tells you the behavior of the liquid. Maldacena's correspondence is that kind of relationship, but exact. The bulk and the boundary are not 2 different systems correlated by magic. They are the same system, written in 2 mutually translating languages. Why does this matter for our question about rules and masters? Because it takes one of the most intuitive intuitions about a higher perspective, the idea that there is an outside view where you can stand and see the whole interior, and turns it into a mathematical equivalence between 2 interior views. From the bulk point of view, you live in a 5-dimensional universe with gravity. You can fall toward black holes. You can measure curvature. You can trace geodesics that weave through interior regions. From the boundary point of view, you live in a 4-dimensional universe without gravity, governed by a gauge theory. You never step inside. You deal only with fields and operators on your surface. Yet, if the duality is correct, neither perspective is more real. They are equally valid, equally complete. No one looking at the whole system from above has to decide which one wins. The choice of description is like a choice of coordinates, more unsettling. In this duality, gravity, the thing that feels most like a fundamental feature of the universe, becomes emergent. The geometry of the bulk spacetime, including its curvature and the presence of black holes, is encoded in the pattern of entanglement and correlation in the boundary field theory. Change the state of the boundary theory, and the shape of the bulk changes. The inside of the can is just a way of rearranging the code on the label. If you take that seriously, the lesson is harsh. What we experience as being inside a universe with gravity may be just one convenient way to arrange underlying degrees of freedom that do not know about gravity at all. From the standpoint of rules, this is just another layer of indifference. You can describe a region with one set of variables, fields, particles, forces, or you can switch to a dual set. As long as the mapping is exact, the system does not care which language you use. There is no special frame where a master sits. In practice, ADS CFT, as the correspondence is called, is technically specific. The original example involves a very symmetric, negatively curved spacetime, not the universe we actually see with its apparent accelerated expansion. The boundary theory has more symmetry than the standard model. Extending holography to more realistic cosmologies is an open, hard problem, but as a proof of concept, it is devastatingly clear. It shows that at least in some worlds, gravity in the interior and a non-gravitational theory on the boundary are two faces of one rule set. It shows that questions about locality, causality, and interior versus exterior can be recast in completely different variables. It shows that the number of independent degrees of freedom in a region with gravity scales with area, not volume, in a fully realized theory, not just in a heuristic. And it shows that this entire structure is forced by consistency. The ingredients that make ADS, CFT possible, are not sentimental. They are technical, supersymmetry, conformal symmetry, specific gauge groups, the behavior of strings in curved backgrounds. You cannot change them arbitrarily without breaking the duality. The space of theories that admit holographic descriptions is narrow, not wide. In that sense, holography is a continuation of the same trend we have been tracing. Wherever we press on the structure unifying forces, quantizing gravity, asking about black hole entropy, we keep discovering that fewer independent ingredients do more work than we thought. In Maxwell's day, light turned out to be an electromagnetic wave. In the age of gauge theories, forces turned out to be the exchange of field quanta. In grand unification, 3 interactions became limits of 1. In string theory, particles became string vibrations. In M theory, string theories became corners of an 11-dimensional framework. Holography adds another step. A space-time with gravity becomes a representation of a lower dimensional system without it. Each move steps further away from a picture where a supervisor might live. Where would such a supervisor stand? On the bulk side or the boundary side? Inside the curved space-time or outside it? On the surface where the dual theory lives? If they intervene in one description, that intervention must have a dual representation in the other. A miracle in the bulk would be a particular, highly structured fluctuation in the boundary fields. A decision to adjust something on the boundary would correspond to a precise reshaping of bulk geometry. The more exact the duality, the more constrained any intervention becomes. You cannot simply nudge the bulk without simultaneously nudging the boundary in exactly the right way to preserve the mapping. You cannot introduce special events that have no echo in the dual picture. Anything that happens must respect the dictionary. In that sense, the holographic framework leaves even less room for arbitrary agency than a single non-dual description. It is not that holography excludes the idea of agency, it just pushes it to more awkward heights. Any putative master must now be a kind of meta-observer who sees both descriptions at once and is constrained by both. Their freedom shrinks as the equivalences grow. Meanwhile, on the technical side, holography has turned out to be a powerful tool for understanding ordinary-seeming physics. It relates strongly coupled quantum field theories systems where our usual perturbative expansions fail to weakly coupled gravitational theories in higher dimensions. That allows calculations in one regime to inform the other. It has been used as a model for quark-gluon plasmas, for certain condensed matter systems, for entanglement entropy in quantum many-body states. In all of these uses, the same pattern reappears. What looks like a messy, strongly interacting quantum system from one view can become a smoother geometric object from another. The geometry is not a separate realm. It is the bookkeeping of correlations. The holographic principle is, in that sense, an existence proof that space and gravity can be emergent from something more austere. It says, at least in some controlled examples, that you can trade geometry for algebra. The universe, in those examples, keeps everything it needs on the boundary. If you let that sink in, the familiar picture of being inside, a vast, three-dimensional cosmos, begins to wobble. Not because something supernatural is peeking in, but because the line between inside and outside is no longer clear. Where are you in a holographic universe? If you identify with the bulk, you inhabit a world with distances and horizons and gravitational redshifts. If you identify with the boundary, you inhabit a world with fields on a flat canvas, evolving according to local rules with no gravity. Both descriptions claim you. Both say, this is a complete account. In practice, we do not know whether our universe is holographic in exactly this anti-de Sitter sense. Observations suggest a positive cosmological constant, more like de Sitter space. The precise holographic jewels for de Sitter spacetimes are not yet as cleanly understood as ADS CFT. There are proposals, sketches, conjectures, no final dictionary. But the existence of one clear holographic duality is enough to change the default intuition. It tells us that dimensionality can be deceptive. That depth can be a way of organizing information, not a primitive feature. That boundaries can carry more physics than interiors. That gravity might be a derived language. You do not have to believe that our universe is literally a projection from a cosmic screen. You only have to accept that the idea is no longer science fiction. It is embedded in serious calculations, in matchings between entropies and correlation functions and spectra. From the narrow perspective of rules, the moral is sharp. Every time we think we have found a place where more is fundamental, more forces, more dimensions, more volume, we eventually discover that much of it can be compressed, encoded, redescribed. The count of independent inputs goes down. The count of internally forced structures goes up. The holographic question, is the universe a projection, is really a question about how far that compression can go. Can 4 dimensions and gravity be rewritten entirely in terms of 3-dimensional, non-gravitational data? Can cosmic history be encoded on a faraway surface? Can the inside of our experience be nothing more than the most efficient way to arrange rules that do not know about inside at all? Those are technical questions at one level, the domain of metric signatures and correlation functions. At another level, they are variations on the same theme that began with a particle wobbling strangely in a ring at Fermilab. How much of what we see needs an overseer? How much can be traced back to constraints, symmetries, and the ruthless tendency of mathematics to reuse the same structures in different guises? The holographic principle does not answer those questions in words. It just draws 2 very different pictures of a universe and insists, through its equations, that they are the same. When 2 very different pictures are forced to be the same, something else quietly comes into view. Not the pictures. The constraints that never let them drift apart. Step back, just a little, from all the names and eras and theories. What we keep finding, in every direction we press, is the same pattern. We write stories about separate things, separate forces, separate particles, separate spaces, separate theories. Then we push on them, and the separations fold. What looked like distinct forces turn out to be the low-temperature faces of a simpler symmetry. What looked like solid particles turn out to be excitations of fields, then vibrations of strings, then modes of higher dimensional branes. What looked like many inequivalent theories become corners of one more rigid framework. What looked like an interior volume turns out to be capturable on a boundary. At each step, choice retreats. At each step, structure advances. If you insist on thinking in terms of a master, this trend is cruel. There is nowhere for a hand to rest. No gap between Maxwell's equations and light. No gap between gauge symmetry and force. No gap between anomaly cancellation and which combinations of fields survive. No gap between the area of a horizon and the entropy it will carry. No gap between a gravitational bulk and a boundary theory once a duality is in place. Anything that happens has to squeeze through those rule gates. You can still imagine intention at the level of why these rules at all. You can place purpose in the choice of the initial conditions, or in the selection of one vacuum out of many, or in the very existence of a mathematical structure capable of hosting a universe. Physics cannot touch that question. What it does touch, over and over, is the expectation that reality should be supervised from the outside. That someone or something needs to keep watch over every orbit, every decay, every fluctuation, to ensure that the whole edifice does not collapse. Nothing in the behavior of the world requires that. One spins process in a magnetic ring. Fields fluctuate in the vacuum. Forces unify and split as temperatures change. Strings vibrate. Brains wrap and intersect. Geometries emerge from entanglement patterns that do not know they are making space. At no point is there a pause where the universe asks, "Should I continue?" From this angle, the cosmos looks less like a machine being steered and more like a program running on hardware it cannot access. A self-executing code whose only decision is to exhaust every path allowed by its own syntax. Self-coding, not self-aware. Once the basic constraints are in place, symmetries, conservation laws, allowed representations, the shape of the action, the rest is downstream. Early conditions flow into later conditions. The variety we see is not a sign of a restless supervising mind. It is the natural bloom of a fixed rule operating in many contexts. That bloom feels personal to us because we live inside it. We are built out of its accidents. Our particular galaxy, our particular star, our particular planet, with its particular chemistry, our particular biosphere, its particular evolutionary accidents, our particular nervous systems, running their own small codes on the substrate that larger codes built. From the outside, none of this is tagged as special. There is no cosmic annotation that says, "Here meaning begins." No flag planted in the equations at the scale of human brains. From the point of view of the rules, a thought is just another pattern of electromagnetic and biochemical activity in a small, warm region of space-time. That sounds cold. It is also a kind of release. If the universe does not assign meaning, then nothing we do can violate some hidden script. There is no correct role we are failing to play, no cosmic job title we are neglecting, no higher agency waiting to grade our performance. Meaning, in that case, is not discovered. It is written, not into the fabric of space-time, but into the tangled interaction between beings capable of modeling themselves and the world, into language, into culture, into memory, into the choices we make about what to care about, knowing those choices are not requested by the sky. The rules that shape us are indifferent. We are not. That asymmetry is easy to miss. We look up, see the vastness, and feel small, as if scale were the same thing as importance. It is not. A galaxy is big and simple. A mind is small and complicated. The universe does not know either exists. We do. There is a quiet reversal hiding there. For almost all of human history, we placed agency above and outside reality. Gods in the clouds, a watchmaker beyond the stars, a cosmic architect leaning over a blueprint. What the physics is hinting at, instead, is a universe where agency is a local latecomer, emerging inside a rule set that does not anticipate it. We are not the reason the laws exist, but we are, as far as we can tell, the only things in reach that can look at the laws and ask what to do next. That is a narrow, precarious freedom. It is also enough. If the universe needs no master, if it runs on constraint alone, then nothing is coming to tell us what matters. No intervention will arrive to correct a trajectory we find harmful or empty. No external judge will affirm that we have understood reality in the right way. We are responsible for the stories we tell about a world that does not tell stories about us. In that light, the indifference of the cosmos is not an insult. It is the condition that makes our small pockets of concern possible. The rules do not care whether we use them to build telescopes or weapons, hospitals or prisons, music or noise. They will support all of those equally well. The difference lies entirely in us. There is, perhaps, one sense in which the universe does care, not about good or evil, not about beauty or suffering. It cares that certain equations balance, that certain symmetries hold or break in specific ways, that certain combinations of fields are allowed and others are not. It refuses to let us cheat there. Every failed theory is a record of that refusal. Every successful one is a record of how much can exist without guidance. Once the rules are tight enough, we happen to live in a region of that record, a place where, for a while, matter cooled into galaxies and stars and planets, and on at least one of those planets, chemistry stumbled into biology, and biology stumbled into nervous systems that can imagine masters and then slowly dismantle the need for them. If there is any conclusion to pull from that without betraying the spirit of the rules, it might be this. The universe does not supervise us. It does not grant us meaning. It does not promise us safety. It offers something else instead. A set of constraints precise enough to build atoms, stars, cells, and minds. A stage where those minds can arise without being asked for, and a silence in which whatever we decide to care about has to be authored from the inside.